Some engines have the oil pressure control for the wastegate actuator managed by 3 controllers, all of which sense compressor outlet pressure. The 3 controllers are an absolute pressure controller, a rate of change controller, and a pressure ratio controller. We've already described the operation of the absolute pressure controller. Here we'll concentrate on the rate of change controller and the pressure ratio controller. The rate of change controller will govern the rate of change of MAP when the throttle is opened rapidly. One particular type of controller limits the rate of change to 6.4 inches of mercury per second. Limiting the rate of change should prevent overboosting the engine as a result of the momentum of the compressor-turbine combination as it accelerates. At high altitudes, the compressor has to use its maximum output to compensate for the low ambient air pressure. Because of this, the temperature of the compressor output is high, often high enough to cause detonation to occur in the cylinders. Typically, the pressure ratio controller will control the compressor delivery pressure at a ratio of approximately 2.2 times the ambient pressure, and will therefore control the temperature of the charge. The pressure ratio controller usually comes into operation above the critical altitude. Additional safety features may be built into some systems. These can take the form of overboost warning lights and an overboost relief valve. If, despite the overboost warning light, the maximum boost is exceeded, then the overboost relief valve will open and relieve compressor outlet pressure to atmosphere. Maintaining a constant pressure at the outlet of the turbocharger up to critical altitude depends on being able to keep increasing the speed of the turbine as the aircraft climbs. We've already stated that this is done by progressively closing the wastegate and diverting an increasing amount of exhaust gas through the turbine. The position of the wastegate is therefore an important factor governing the performance of the engine. The position of the wastegate throughout the running of an engine from start to above critical altitude, the engine power output, the turbine speed, and the manifold pressure are all shown in this graph. Prior to start, the wastegate must be opened to allow the free flow of exhaust gases to atmosphere. Otherwise, the engine would be very difficult, if not impossible, to start. To achieve this, the spring in the wastegate actuator forces it fully open. Immediately after start, there is probably not enough exhaust gas to spin the turbine fast enough to create the pressure required by the system designer at the outlet of the compressor. The aneroid capsule in the absolute pressure controller will therefore be expanded, closing the bleed valve, trapping oil within the wastegate actuator, causing its piston to close the wastegate fully. As the throttle is opened, sufficient exhaust gas will be produced by the engine to turn the turbine fast enough to enable the compressor to achieve more than the required pressure at its outlet. This increased pressure is sensed in the aneroid capsule in the absolute pressure controller, and oil is released through the bleed valve from within the wastegate actuator, thus allowing its internal spring to start opening the wastegate. The wastegate will continue to open as the throttle is opened, until at full throttle at sea level ISA pressure it is almost fully open. The wastegate has to be able to open a little further than the position it assumes on an ISA day at sea level to cater for those days when the ambient pressure is greater than ISA. Without the ability to open further, there would be no way to reduce the turbine speed and thus maintain the compressor outlet pressure within limits on those high ambient pressure days. From the moment of takeoff, and throughout the climb, the pressure at the compressor inlet falls, causing its outlet pressure to fall also. This drop in outlet pressure is signalled to the aneroid capsule in the absolute pressure controller, which progressively closes the bleed valve, increasing the pressure of the oil in the wastegate actuator, causing it to gradually close the wastegate. Eventually, an altitude will be reached where the wastegate will be fully shut, and no more increase in turbine speed is possible. This altitude is termed the critical altitude. From now on in the climb, the outlet pressure of the compressor will fall, and the inlet manifold pressure and engine power output will fall in sympathy. Of course, the engine power output will have been decreasing with every foot of the climb from the moment of takeoff. This is typical of a turbocharged engine, but as we saw earlier, after critical altitude, the rate of decrease gets greater, approximating that of a normally aspirated engine. As you can see from this graph, the power developed by the normally aspirated engine is at a maximum at sea level, and progressively decreases as altitude is increased. The power developed by an otherwise identical but supercharged engine at the same RPM and manifold pressure is less than that of the normally aspirated engine at sea level. This power loss represents the power required to drive the supercharger. However, as height is increased, the power developed by the supercharged engine at constant throttle settings increases as a result of the decreased temperature of the atmosphere. The decreasing temperature causes the density of the air to fall less rapidly than it otherwise would if the temperature stayed constant or even increased, and thus a greater weight of air is pumped into the cylinders for the same manifold pressure. The decrease in air pressure experienced in the climb also causes less back pressure on the exhaust, thus improving scavenging of the cylinders and the efficiency of the engine. Internally driven superchargers are generally used on medium and high-powered piston engines, approximately 250 brake horsepower and above. They're fitted downstream of the throttle valve. Just as with the externally driven turbochargers, the most common form of compressor used in the internally driven supercharger is the centrifugal compressor. The compressor impeller is made as light as possible from magnesium or aluminium high-strength alloy. A shaft, splined into the rear of the crankshaft, provides the initial drive to the supercharger impeller. Notwithstanding the lightness of the compressor impeller, because of the high rotational speeds at which it operates, up to 25,000 RPM in some cases, the inertial forces generated during engine acceleration and deceleration are huge. To minimize the inertia stresses in the impeller drive, some of the systems incorporate a spring drive unit. This transmits the drive through intermediate gears to the impeller pinion, and limits the high torque impulses transmitted to the supercharger impeller during high rates of propeller engine acceleration or deceleration. Historically, the superchargers of some high-powered engines have been driven at 2 speeds, in order to save power at low altitudes. The low speed, or MS, moderate speed gearing, is used at low altitudes, where the atmosphere is relatively thick, and the high speed, or FS, full speed gearing, used at high altitudes, where more effort is required to compress a comparable weight of mixture. This graph compares the outputs of 3 engines. The first is normally aspirated. The second has a single-speed supercharger, and the third has a 2-speed supercharger. Some high-powered superchargers have also been fitted with 2 impellers working in series, in order to raise the overall compression ratio. Notice the addition of an intercooler after the second stage of compression. When used in general aviation aircraft, internally driven superchargers normally employ a single impeller, driven at a fixed speed relative to the crankshaft, usually between 8:1 and 12:1. This type of supercharger is capable of maintaining sea-level manifold pressure up to an altitude of between 5 and 10,000 feet, at rated power settings, depending on the gear ratio. Since a supercharger is designed to compress air and provide sea-level pressure or greater in the induction manifold when atmospheric pressure is low, excessive manifold pressure could be produced when atmospheric pressure increases, especially in a rapid descent like the one depicted on screen here. It's necessary, therefore, to restrict full throttle opening when the aircraft is operating at heights below full throttle height, and, to relieve the workload on the pilot, This is often done automatically. There are two controls that affect the pressure developed by the supercharger. They are the throttle lever position, within the limits imposed by full throttle height, a term which will be explained shortly, determines the boost pressure that is delivered by the supercharger. The throttle is, in effect, a boost selection lever, and, together with the propeller control lever, determines the power output of the engine. Almost without exception, variable pitch propellers are installed on supercharged aircraft engines. A variable pitch propeller allows the propeller blade angles to be adjusted in flight between fine and coarse limits. This results in the RPM of the engine increasing or decreasing. Thus, the propeller pitch control lever can be said to be an engine speed control, and, as the supercharger impeller is driven by gears from the crankshaft, any change in engine speed will result in a corresponding change in the speed of the rotation of the compressor impeller. Having said this, if the engine is fitted with an automatic boost control unit, then the boost pressure reading will essentially remain constant at whatever is set by the throttle lever, while the engine RPM changes independently. Two-speed superchargers may have automatic or manual gear selection, which allows the use of moderate gear for low altitudes and a higher gear for greater altitudes. Where manual selection is used, the pilot is provided with either a mechanical push-pull selector or a two-position electrical switch. The selector or switch will be marked MS for moderately supercharged and FS for fully supercharged.